Good morning, and welcome to this session covering building embedded devices with Arm SystemReady-IR. It's great to have you all here. I am Olivier Bernard. I'm the Director of High Performance IoT, and I will be joined by Grant Likely, our Senior Software System Architect. Grant and I are very excited to share with you an update on this critical Arm program. Now, looking at the IoT plays an increasingly crucial role in supporting diverse use cases with a range of power and performance requirements on compute platforms, which are already deployed in the field. Now, for years, the IoT industry has deployed IoT solution using a model of transmitting raw sensor data to the cloud, where the intelligence and storage was located, where you had infinite compute powers, and you could create your models, you could create your analytics, get your insight. However, as we scale to 1 trillion devices, that model is no longer sustainable because of the sheer amount of data being generated and needed to be moved through the infrastructure. And that infrastructure is unable to scale as fast as the number of application devices being deployed. So to deliver sustainable services at scale, the IoT must embrace cloud native software principle consistently and securely, enabling distributed compute module from the cloud to endpoint and deploying intelligence at the edge, closer to the data source. Cloud native technologies empowers organizations to build and run scalable applications in modern, dynamic environments such as public or private and hybrid clouds. And now we're moving all this to the edge. Containers, service meshes, microservices exemplify this approach. And to do that, we need consistency and compatibility across the entire ecosystem. And that is why Arm announced Project Cassini in 2019. It is an industry-wide initiative enabling the migration of workload from the cloud closer to the data at the edge, while creating consistent and more homogeneous deployment model for an applications. Project Cassini addresses the two major roadblocks to IoT deployment: scalability, which I referred to before, and fragmentation. And it does provide the evolution of IoT deployment model that is needed. We need to make it simpler to scale and reduce the complexity of deploying software, a model just like in the cloud that just works. Now, you can see on this slide, Project Cassini is an umbrella program that covers three distinct vectors. In yellow, you got a robust set of standards leveraging software, but allowing and celebrating hardware diversity. This set of standards is called Arm SystemReady, and it addresses the ecosystem fragmentation challenge that we're solving. And that's what we will talk mostly about today. In blue, we address security, and we've set up security APIs and certification program that can be trusted by developers across workload and ecosystem. And then the last part at the bottom is the ecosystem, and it's cloud native software stack, reference use cases, blueprints designed to accelerate implementation and time to deployment. In other words, this is what we need to accelerate the path to deployment and monetizations. Now, when it comes to standardization, there's always a challenge between a system that is extremely versatile, but usually high in customization and therefore expensive in maintenance cost for software. And that's on the right. Or you can have some very stringent standards that are commonly and consistently adopted by all. But these usually come at the expenses of flexibility. And in most cases for IoT, it just doesn't work. There's just too many devices, too many applications, too many deployment for that to work. So here, the key is to optimize that value and establish the right compromise. And it is to achieve that balance that we decided to create 4 different personas or bands for system-ready standards to address those specific markets. The 4 bands are server-ready, which, as the name implies, addresses the server market. Embedded server, which is more applicable to the embedded space close to the edge of the infrastructure. IR is the IoT ready band, and then LS is Linux boot, which is for cloud service providers. So said in another way, in this graphical representation, just like I presented earlier, This gives you an idea of where those different bands fit. As you can see on the right side, the server is the cloud. As you move towards the endpoint, you can see that we're moving to infrastructure edge and 5Gs. And that's where the embedded servers, the more enterprise grade operating systems belong. And as you move further away to IoT gateways and device gateways, smaller compute platform, that's where the IoT ready band stands, the IR. Now, in this slide, also, what I want to point out is the coverage of ARM Project Cassini. And you can see here that it doesn't cover the whole IoT landscape. It only covers application processors, or Cortex A in our lingo. If you're looking for MCUs or Cortex M type devices, we have another initiative called Project Centauri that provides sort of the same unification and monetizations of IoT deployment. But Project Cassini is all about Cortex-A, and that graphic here shows you the range of application it will cover. So to go and focus now on system ready, one of the unique challenges in IoT is the breadth of application and the wide range of hardware applications and implementations that are provided by silicon suppliers and ODMs/OEMs. So what we really want to do here with system ready in a centerpiece is we want to decouple and disassociate the choice of hardware from the choice of software and application. What we want to do is we want to make sure that everyone chooses the right hardware solution based on memory, compute power, interfaces, application feature set for your application without having to really be constrained by the kind of workload or applications of software operating system you will run. Choose the perfect hardware for your application. And with System Ready, which offer a range of system software and firmware, you can land any operating system, any container, any hypervisors on those devices, and you can focus on the best solution for the hardware and the best solution for the software. So one of the reasons we call this initiative, Project Cassini, an industry-wide initiative, it's because in order to gain momentum and achieve critical mass, we really need to work with members of all levels of the IoT value chain, from silicon maker, the SIPs, to ODMs and OEMs, making the hardware, through software and OS vendors, to delivery services, system integrator, and even infrastructure enablers such as the cloud service providers or major network operators or people operating like AT&T. It takes many actors to design, deploy, and manage IoT systems. And Project Cassini has been designed having in mind that objective of offering a solution and value to all of these actors. And with this, you can see from this side that we've achieved real tangible progress over the last year, with silicon partners providing certified silicon devices supported by a BSP that includes all of the firmware and patches and configuration needed to support full certification. That's why we got NXP and Rockchips as certified silicon partners, to ODMs and OEMs that have used those BSPs and are going through or went through the certification process. So what's really impressive when you look at this slide is the breadth of additional partners that are either nearing certification or preparing their hardware for it or already passed certification. We now have well over 50 IoT partners involved in the Arm SystemReady-IR program. So that's real tangible success with a program that's only at the end of the second years. And the program is a 4-year program overall. So now to go through the detail of what it takes to become an Arm SystemReady-IR certified product, or how to participate, understand what the value it offers today, and what our long-term view of the program is. Allow me to introduce you to Grant Likely, our senior system software architects leading the technical aspect of the program. Grant, on to you.
Great. Thank you very much, Olivier. It is great to be here to talk about this today. So I want to talk about what System Ready IR is and why this brings value and like the details of it. But before I can do that, I first need to spend some time talking about what it looks like just in the normal way that we produce embedded devices, and specifically embedded Linux devices. Um, Now, when we're building a product, more often than not, it is we take a bunch of components. We take the Linux kernel, we take U-boot, we take the board that it's going to be running on, along with any vendor SDKs, the applications that run on top, or hypervisors, and custom I/O that might be there. We put it through the engineering process. We turn the crank, and out at the end comes an OS image that will run on that hardware so that we can ship a product. Then, when we want to change something, new version of Linux, different app, turn the crank again, new configuration, new image comes out the bottom. And we do this again and again and again, regardless of what changes. And each time we turn the crank, we've got a new configuration that needs to be supported. And it becomes a little bit like Groundhog Day, where we're doing the same thing over and over again. Now, let me be clear. The embedded Linux market is incredibly healthy, and there are hundreds of thousands of different designs that are out there that we're building, that we're able to do and support. But there's more that we can do to really expand this market and expand the capability that we have in embedded Linux devices. And that's what we're going to talk about here with what we can do to reduce the amount of engineering that's required in order to change configuration and manage all of the different configurations of devices. So if we're going to create a standard platform and make it easier to land applications and software onto the platform, it turns out that there's some relatively well-defined constrained changes that can be made to the way that we approach architecture design. So over on the left-hand side here, we have the traditional embedded Linux flow, where we have all the components. We usually use Yocto to pull all of it together and create a configuration that comes out. Now, this is a monolithic image, but there's a few changes that we can make. Now, to be able to separate the operating system and applications from the platform itself. And there's three things that I'm going to highlight here. The first one is the UEFI ABI. Typically in U-boot, we have U-boot boots the Linux kernel, and the platform is modified. The U-boot is modified for the platform, and then when you build your OS image, it is tailored for how U-boot boots on that platform. What the UEFI ABI brings in is it brings in a consistent way of actually booting the platform so that the OS doesn't need to know details on how the platform boots or finds the OS. It also gives us an ABI that allows us to have optional UEFI applications in the pre-boot environment before we actually get into Linux, a consistent ABI that allows them to use services of U-boot to, say, change the configuration of boot variables, to update the security information, update firmware, and or provision the device by going out to the network to fetch a new image. Right, so by bringing in the UEFI ABI, we've got consistency. We can create consistency on the platform interface. The second thing is to take the flattened device tree, and on the embedded Linux platform, the flattened device tree is the system description. It's how Linux knows what hardware is there and how to initialize and use it. What we can do is, rather than treating the device tree as part of the Linux kernel itself and tied closely to that, we can move the device tree down into U-boot so that firmware actually provides a default or standard device tree to the operating system. And then what this does is now your operating system no longer needs to know details about the hardware that it's running on ahead of time. You can create a generic Linux image that will boot on any platform as long as the correct drivers are installed. And then the third thing that we can do to create a platform is actually mandate a way to do updates to the platform without the operating system needing to know the details. And right, I mean, if we're trying to build secure, always-on connected devices, those devices aren't going to stay secure, connected, and always on very long if they're full of security holes. And we're not going to maintain security if we're not able to update the firmware. So we have standardized, or if we standardize the firmware update interface so that Linux or the operating system that's sitting on top can update without having to know details on how it's done, we just increase that platformization. And so what that does with those three changes, we now have a really nice separation between what the platform does and what the OS does. And it gives us the ability to use the existing tools. So we can still use Yocto, we can still use all the things that we're familiar with, but we've got that separation, and it allows us to do uh, different things with the OS as what we do on the firmware. So that's the changes. Those are the things that we are looking at doing. Now I want to talk about the SystemReady IR program, and specifically how the IR program helps to simplify your engineering using those changes that I just talked about. So SystemReady IR really brings in four things. The first one is consistency. It brings consistency to the platform so that the OS doesn't need to deal with platform-specific behavior every time it's landed on something new. We do that with a standard boot flow by adopting the UEFI ABI. We do this, by adopting the UEFI ABI, it means that we're using exactly the same interface that's used in other parts of the computing ecosystem. It's the interface that's supported by the top tier Linux distros. So it actually opens up these embedded platforms, not just to reducing the engineering required if you're doing a custom Linux build for the product, but also if your product happens to use one of the third-party distros, um, including Ubuntu, Debian, Fedora, and OpenSuse. Um, the other thing that we do is the SystemReady IR program guarantees that the platform will boot mainline Linux, which will, again, reduces the amount of engineering required. You don't need to go and find a platform-specific tree in order to boot on the platform. SystemReady IR, because we test with Linux, guarantees that Linux support for that silicon and for that board has already landed in the mainline kernel. The second thing that it brings is self-describing. Self-description. And I talked about moving that device tree from being tightly tied to the kernel, to Linux, and to move it into U-boot, into the firmware. By doing this, the platform now becomes self-describing. And it means that the OS image doesn't need to carry around information about the platform. So if you have an OS image and you have, say, multiple products that really use the same OS and the same applications on top, you're able to support a wide variety of hardware platforms with just that single OS image. And in fact, if you go and look at Yocto and use the ARM meta layer and build the def config, you've got a platform that is system ready compliant, or that will run on system ready compliant hardware. The other really interesting thing that this does is, because we're using standard interfaces, you can actually build your OS image. You can test it in the cloud on virtual machine instances, and then deploy that exact same image out onto hardware. All the interfaces support that. Third one is maintainability, and this is all about the update of firmware using Update Capsule and the ESRT. Again, these are industry standard technologies that are already in use. So we're just making use of the same tools. It works with firmware upd, it works with LVFS, it also works with firmware update and management platforms that are used for some of the embedded Linux OSs. And once again, this decouples the details of how firmware does its job from the OS. And that's all the functional things that SystemReady IR does. Then finally, SystemReady IR brings reliability and assurance. So it's great to bring in all of this functionality. It certainly simplifies engineering, but it's not valuable. It's not going to be very useful if we can't know that it actually is compliant with the interfaces. So part of SystemReady IR is we're bringing in compliance test tools. We have an architecture compliance suite that goes and tests all of the interfaces that are used. We have a program with third-party labs for a platform that is system ready, that wants to be system ready compliant, will be tested, verified. And so if you see a system ready IR mark on a platform, if you're a ODM, it is something that you can use to market so that your customers know what they're getting. And if you're looking to build products, it's something that you can look for from your SIPs or ODMs, so that you can choose a product that's not going to require a lot of engineering to get up and running. Now, having said that, we're bringing in standards, but as I've said before, the embedded Linux ecosystem is very robust. We've got a lot of technology that is mature and has adopted. So it would be no good if we came in with SystemReady IR and said, wait, you need to change everything in order to bring in these standards. Instead, this entire program is designed to work with what we're already using. The device tree and U-boot are well established within the embedded Linux ecosystem, and SystemReady IR works with that. What we've done, the UEFI ABI has been implemented as part of U-boot. So if you're using a recent version of U-boot, it is just a set of configuration options to turn on all that functionality. Same thing with device tree. To have a copy of the device tree in U-boot is fully supported. U-boot uses device tree internally, and it provides that platformization without requiring wholesale changes to your engineering process. And then that just brings in compatibility with shim, grub, systemd boot, with Linux UEFI, the UEFI stub in Linux, and a lot of the other technology that makes use of that. Also, it simplifies the Linux deployment by reducing a lot of the custom engineering that we tend to do per platform. And we've tended to do it per platform just because there hasn't been any driver that really brings things together. And that's part of what we're hoping to do with the SystemReady IR program, is to bring together consistency where there's no need to differentiate, where there's no need to do something differently. And as I've said before, that just opens up the market. Not only can we keep doing custom Yocto or OpenWRT, but we're also easily able to boot unmodified the top tier distros. We're compatible by design as well. So we wanted to not just be compatible with what the embedded ecosystem is doing, but also with what the rest of the ARM ecosystem is doing. So wherever possible, we're using the same technology. UEFI is across the SR, ES, and IR bands of SystemReady IR. And so this allows us, as I said, we can boot an image on multiple different platforms. The Yocto meta layer will boot on SystemReady SR, ES, and IR platforms, all without configuration changes. We've got the testing process that is designed. If there's an image that can be downloaded, that will boot on any platform that has mainline support. And so that is open source and it's available for you to go and play with and test and make sure your board's up to is working correctly. And we're seeing like really wide interest in this platform. I mean, we've got 9 platforms certified now. By the time you see this, from when I've been recording it, you can expect to see more platforms, and there'll be even more before the end of the year. Okay, right, so what do you do now? If you're interested in this program, we have a very simple process to get to certification. And that process is, first of all, just contact us. Let us know that you're interested. There's an email address on this slide deck that you can get a hold of us. We will get you to run some of the pre-certification tests and prove that or to make sure your platform does what it needs to. Then you can go and run. We will take those results and provide it to one of our testing lab partners, and they will then do the evaluation of the kit to certify or to verify the results. And once we look at the verified results, we will be able to issue a certification or send it back and say, here are the things that need to be fixed before we move on. That certification program is running now. You can go to the ARM website to see the details and the list of the certified platforms. Also, if you want to be involved with this and help to define what's coming up in SystemReady IR over the next year, join us in the EBBR community. The SystemReady IR is undergirded by the EBBR spec, and that is being run as an open source or as a community project that anyone can be involved with. And then finally, there's the email address, systemready@arm.com, if you want to contact us about this program. And then I also want to highlight our certification partners. These are the test labs that are actually validating that platforms are behaving correctly. That's the University of New Hampshire, Global Logic, Capgemini Engineering, and Linaro. And I just want to right now, big shout out to Linaro. All the technology that we're using in SystemReady IR, Linaro has done an incredible amount of work to enable and mature and get those platforms working. And then finally, just as I wrap up, I want to say this is SystemReady IR 1.0 is a great start. It gives us a really solid foundation that you should be able to make use of right away. But it's not where we're stopping, because we want to see this program grow and bring in more features that will help to just make the embedded Linux ecosystem more robust. So the places we're investigating: UEFI secure boot, authenticated firmware updates. We're looking at stability of the device tree so that we can have backwards and forwards compatibility with kernels, and the features that are needed for over-the-air provisioning. A lot of this work has already begun in U-Boot, and so now we're looking at how we would bring it into the program. So what features do you want to see? Please get in contact with us, join us on the EBBR bi-weekly calls, and help us to define SystemReady IR 2.0. And that is it. Thank you very much for your time on listening to me and Olivier here today. I would like to take a moment to highlight a couple of other sessions. If you're interested in Yocto and how you land Yocto on SystemReady IR, please go watch John Thompson's talk that he goes through the details of exactly how that works. And there's also Dong Wei's What's New in SystemReady that will give a greater overview of the program. And then there's also the keynote, It's Time for 10 Times the Internet of Things by Mohammed Awad. And we also have a Tales from the Edge Project Cassini panelist. And with that, thank you very much, and I hope you enjoy the rest of the conference. There's a live Q&A session starting now to continue the conversation. To take part, join us on Zoom by clicking the yellow button just below the video player on this session's page.